Astronomers just found a black hole that had been hiding in plain sight for over 20 years, sitting inside a pile of data NASA's Hubble Space Telescope had already collected, just waiting for somebody to notice it. Nobody needed to launch a new mission. Nobody needed to point a telescope at anything new. The evidence was already sitting there in the archives the entire time, and it took a genuinely clever piece of detective work to finally drag it out into the open. Stick around, because this discovery solves a puzzle astronomers have been chasing for decades, involves the longest-lasting black hole partnership ever recorded, and turned up a result nobody actually expected once they found it. If you want to keep following stories like this one as they develop, go ahead and subscribe before we dig in. The story centers on Omega Centauri, the largest and one of the oldest star clusters anywhere in the Milky Way. A dense, glittering ball containing roughly 10 million stars, all gravitationally bound together and orbiting a shared center of mass. It sits about 18,000 light-years from Earth and is visible to the naked eye from dark enough skies, particularly in the southern hemisphere, appearing as a fuzzy, faint smudge long before any telescope reveals it for what it actually is, an entire miniature galaxy's worth of stars packed together in an almost impossibly dense ball. Some astronomers actually suspect Omega Centauri might not be an ordinary star cluster at all, but rather the stripped-down core of a much larger dwarf galaxy that was slowly torn apart and absorbed by the Milky Way's gravity over billions of years, leaving only this dense central remnant behind, still orbiting our galaxy as a satellite of sorts, rather than ever having fully dissolved into it. Clusters like this have been a genuine source of frustration for astronomers for decades, and the reason comes down to some fairly basic stellar physics. Massive stars burn through their fuel quickly and dramatically, and when they finally run out, many of them collapse and explode as supernovae, often leaving behind a stellar mass black hole in the wreckage. Given how many stars are packed into a cluster like Omega Centauri, and given how long it's been around, models have consistently predicted that this cluster should be home to somewhere around 10,000 stellar mass black holes, a genuinely enormous hidden population. And yet, for as long as astronomers have been looking, actual direct evidence for any of them has been almost completely absent, an obvious mismatch between what theory predicted and what anyone had actually managed to confirm. That changed on July 13th, 2026, when a research team, led by astronomers, including Maximilian Haberle of the European Southern Observatory and Matthew Whitaker of the University of Utah, published their findings in the astrophysical journal Letters, using more than 20 years of archival Hubble Space Telescope data, spanning observations collected all the way from 2002 through 2023, combined with newer, sharper measurements from the James Webb Space Telescope. The team finally confirmed the first stellar mass black hole ever detected inside Omega Centauri. It's been given the fairly technical name Omega Cat BH2, and finding it didn't require spotting any dramatic burst of light or explosive event. It required something far more subtle and honestly far more impressive once you understand exactly how it was done. The technique the team used is called astrometry, and the basic idea is elegantly simple, even though the execution demands an enormous amount of precision. Rather than looking directly for a black hole, which by definition emits no light of its own and is effectively invisible, astronomers instead track the motion of a visible star that happens to be gravitationally paired with one. If that visible star appears to wobble slightly in a small, regular repeating orbit, tugged back and forth by the gravity of something nearby that nobody can actually see, the mass and behavior of that unseen companion can be calculated purely from how the visible star moves. It's a bit like watching a dog on the end of an otherwise invisible leash, and figuring out exactly how strong and how far away whatever is holding that leash must be, based purely on how the dog gets pulled around. This kind of measurement demands a genuinely extraordinary level of precision, since the actual positional shift being tracked amounts to a fraction of a pixel's worth of movement across Hubble's camera, repeated and confirmed across dozens of separate observations spanning more than 2 decades, simply to build enough confidence that the wobble being measured is real and not just noise or measurement error creeping into any single image. By sifting through more than 2 decades of accumulated Hubble images and carefully tracking the position of one particular star inside Omega Centauri across all of that time, the team detected exactly this. Kind of subtle gravitational tug, then brought in Webb's more precise, near-infrared measurements to refine and confirm exactly what they were seeing. What they found orbiting that visible star turned out to be genuinely surprising in more ways than one. The visible companion star itself has a mass of about 0.78 times that of our Sun, a fairly ordinary, unremarkable star in its own right. Its invisible partner, however, turned out to be considerably heavier, checking in at roughly 4.46 times the mass of the Sun, definitively too massive to be a neutron star. The other type of extremely dense stellar remnant that can form when a massive star collapses, and squarely within the range that can only be explained by an actual black hole. That distinction between a neutron star and a black hole matters quite a bit to astronomers, and it comes down to a fairly firm physical limit. Neutron stars are incredibly dense, but there's a ceiling to just how massive one can get, generally understood to sit somewhere around 2 to 2.5 times the mass of the Sun, before the object's own gravity overwhelms even the extreme quantum forces holding neutron star material together, causing it to collapse further into a black hole instead. At 4.46 solar masses, Omega Ket BH2's invisible companion sits comfortably above that ceiling, leaving black hole as the only remaining explanation consistent with the data. This wasn't actually the first time scientists had studied this particular pair of objects either. An earlier team, studying the same binary system, had proposed it might contain a neutron star rather than a black hole. But by expanding the amount of Hubble data analyzed and adding in Webb's improved precision, this new team was able to definitively rule that possibility out and settle the question with considerably more confidence than before. Here's where the story gets genuinely unexpected. Given the environment this black hole is sitting in, a dense, ancient, and notably metal-poor star cluster, meaning one relatively lacking in the heavier elements that get forged inside earlier generations of stars. Astronomers generally expect any black holes forming there to end up on the heavier side, since stars in that kind of low metal environment tend to lose less mass through stellar winds before they eventually collapse, leaving more material behind to form a correspondingly heavier remnant. Anil Seth, a co-author on the study from the University of Utah, described this result as genuinely surprising and exciting, precisely because Omega Ket BH2 came in noticeably lighter than what that kind of environment would typically be expected to produce. Rather than confirming existing expectations, the black hole ended up quietly challenging them instead. There's another genuinely remarkable detail buried inside this discovery, one that has nothing to do with the black hole's mass at all. The orbital period connecting this black hole and its visible star companion turned out to be the longest ever recorded for any known black hole binary system. That's a meaningfully unusual result on its own, since most previously confirmed black hole binaries tend to involve much tighter, faster orbits, largely because those are simply easier to detect using more conventional observational methods. Finding a black hole locked into such an unusually wide R-slow orbit is exactly the kind of system that would have been extraordinarily difficult to identify using older detection techniques, and it's a genuinely good demonstration of why this particular astrometric approach, patiently tracking tiny positional wobbles over the better part of 2 decades, was necessary to catch it in the first place. It's worth pointing out that this isn't actually the first major black hole-related discovery to come out of Omega Centauri in recent years either. Back in 2024, a team working with much of the same underlying Hubble data identified 7 unusually fast-moving stars clustered near the very center of Omega Centauri, providing strong indirect evidence for a completely different category of black hole, an intermediate mass black hole estimated at over 8,000 times the mass of our Sun, sitting at the cluster's core. Intermediate mass black holes occupy a genuinely important and still poorly understood place in astrophysics, sitting in a size range between the smaller stellar mass black holes formed by individual collapsing stars and the truly enormous supermassive black holes, found at the centers of entire galaxies, including our own Milky Way. For a long time, this middle category existed almost entirely as a theoretical prediction, since astronomers had confirmed plenty of stellar mass black holes on the small end and plenty of supermassive black holes on the large end, but had struggled to find solid, direct evidence of anything convincingly sitting in between, leaving a genuinely awkward gap in an otherwise fairly well-organized picture of how black holes come in different sizes. Finding solid evidence of an intermediate mass black hole at Omega Centauri's center back in 2024, and now finding direct confirmation of an individual stellar mass black hole within the same cluster in 2026, gives researchers 2 genuinely different complementary pieces of evidence about the full range of black holes potentially hiding throughout this one remarkable star cluster. There's also a reason this particular black hole mass range matters well beyond just Omega Centauri itself. Astronomers studying black hole mergers using gravitational wave detectors like LIGO have noticed something curious over the past decade of observations, a genuine scarcity of detected black holes sitting in roughly the same mass range that Omega Ket BH2 falls into. Gravitational wave observatories work by detecting the extraordinarily faint ripples in space-time itself produced when 2 extremely massive, extremely dense objects, like a pair of black holes or neutron stars, spiral together and eventually merge. Over roughly a decade of these detections, researchers have built up a genuinely large catalog of confirmed black hole mergers, and that catalog has revealed a noticeable dip in how often black holes show up in exactly the few solar mass range where Omega Cat BH2 sits, a gap that has puzzled astrophysicists trying to model how black holes of different sizes actually form and evolve. Finding a confirmed example of a black hole at exactly this mass, sitting quietly in a stable, long-period binary rather than merging violently with another object, the way gravitational wave detectors typically catch black holes, gives researchers a genuinely valuable data point for understanding why that particular mass range has shown up so rarely in gravitational wave surveys so far, and whether that scarcity reflects something real about how these black holes form, or simply reflects a blind spot in how current detection methods are built to find them. Haberle, one of the study's lead authors, made a point of highlighting something that goes well beyond the specific scientific result itself, describing this discovery as a genuine demonstration of the immense legacy value locked inside the Hubble Space Telescope's archive. Hubble has been continuously collecting data since its launch back in 1990, accumulating well over 1.7 million individual observations across more than 3.5 decades of operation. A huge amount of that archive doesn't get fully exploited the moment it's first collected. Instead, it sits quietly available for any future researcher clever enough to ask a new question of it, using techniques or comparisons that might not have even existed yet when the original images were taken. This particular discovery is a genuinely clean example of exactly that process in action. A black hole that had effectively already been photographed, indirectly, over and over again across more than 2 decades of Hubble images, simply waiting for someone to notice the pattern. So here's where all of this actually lands. Astronomers went looking for one of roughly 10,000 black holes that theory has long predicted should be hiding inside Omega Centauri, and after decades of coming up empty, they finally found one, not through any dramatic new observation, but by patiently tracking the subtle wobble of a single ordinary star across more than 20 years of archived Hubble images, then confirming it with a fresh look from Webb. What they found wasn't quite what anyone expected either, a lighter than predicted black hole locked into the longest-lasting orbital partnership ever recorded for a system like this. It's a genuinely satisfying example of how much more science can still be squeezed out of a decades-old space telescope simply by asking a smarter question of data that was already sitting there the whole time. If you want to keep following along as researchers keep combing through Hubble's archive for more of these hidden black holes, make sure you're subscribed with notifications turned on. Drop a comment letting me know whether you think there are more surprises, like this one, still waiting to be found in old telescope data. And share this with anyone you know who'd be amazed to learn a 20-year-old photograph can still be hiding a black hole nobody had noticed yet.